Hi guys, this is Jonathan Lambert from the Mathematics Development and Support Service at National College of Ireland, and this is my first, I suppose, live or online presentation. So it would be great maybe if you had a little bit of patience with me, just through this particular session. But what I'm going to do is, first of all, is before I suppose kick off, is I'm just going to say hi through the hi. Oh, that's very loud. I'm just going to say hi through the chat window, and just to see who I have out there. So I'm going to say hi, hi. This is Jonathan. Just to see who I have with me now. So it'd be great maybe if you can maybe just say hi back. So then I'll know who's in on this live feed. Uh, sure. With that said. You can probably do that yourselves. This particular live session is all about number systems. I have had a couple of emails from students here within NCI in relation to number systems and the conversion between number systems, and they have asked would I do this particular session. In particular, we're looking at binary number systems, octal, decimal, and hexadecimal number systems. Uh, so I actually have Owen there. Brilliant. Hi, Owen. Hi, Owen. I hope you can hear me. I hope you can hear me. Uh, if you can, please say yes. Okay. Okay, I'll just send that off there. There's Christoph as well. Hi, Christoph. It's great to have you here. Hi, on. Great to have you here as well. So just waiting just to make sure that the sound is all perfect. Doesn't seem to be any problem in relation to the camera setting. Everybody's seeing that okay. And also just in relation to the sounds that you can actually hear me talking. Yeah, it would be great. Chris, sound is okay. Thanks, Christoph. That's brilliant to hear. So what I'm going to do now is I'm just going to proceed with this particular lesson. Look, there's many different ways to convert between these particular base systems, but the most important thing that we're dealing with is that these are what's known as positional number systems. And before I get going, I just really want to define what we mean by these number systems in relation to the digits that we can use in relation to creating numbers from the systems. So this is like an introductory. This is an introductory lesson. So if you are here, I'd hope you're here for this introductory stuff. There's Thomas as well. Hi, Thomas. All good. So just in relation to binary, and I'm sure you know this from class, the binary system, it's called a base two system. A base two system. What we mean by a base two system is that there's only effectively two digits that exist in the world of binary. Okay, and we probably know this, and everything being computer related nowadays, and everybody talking about code and so on. The binary system or the base two system is the numbers within that system are only composed of numbers that contain zeros and ones. Okay, so the digits have to be taken from this particular set of zeros and ones. Okay, in relation to the octal number system, octal. Okay, uh, Octal is what's known as a base 8 system, so it's base 8. And well, as the name suggests, there's 8 symbols in that particular system. So that system is composed of zeros, ones, twos, threes, fours, fives, sixes, and sevens, all the way up to 7. Yeah, I remember when I was first learning these systems, and I say, "No, base 8, so it must go up to the digit 8." But no, there's 8 digits in it. And you see, we're starting at 0. That's our first, our second, our third, our fourth, our fifth, our sixth, our seventh, our 8th digit in the system. So it goes from 0 inclusive up to 7 inclusive. In relation to base 10, which is our decimal numbers, okay, the number system that we're most familiar with working with, the decimal numbers, this is known as base 10, okay, and the digits are the well-known digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and up to 9. So there's the 10 digits. That's the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, the 10th. So if you want to create numbers in decimal or decimal numbers, you can only take digits from this particular set of numbers. And then finally, especially in computing, what's really important is what's known as hexadecimal or hex. Let's call it hex, which is base 16. And what that is that's numbers composed of digits taken from a set that contains 16 digits. And you can see it's going to contain all these digits here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there has to be another one and another one and another one. We need 16 of them. We've only got 10 here, so we're missing 6 of them. So we need a new digit, and we want a digit that's not going to be formed from any of the previous digits. So the new digit, we'll say the first one is A, followed by B, C, D, E, and F. You actually see now that this gives us a set of digits, which is 16 digits. The first, the second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 16 digits. Okay. So effectively, numbers, binary numbers, let's say, are numbers that are taken from this particular set. So you can choose. No, we can't start with zeros. Okay, we can't start with zeros if it's padded out. But let's just restrict it for the moment. Yeah. So let's say our numbers might like we could have a binary number with a certain amount of bits. Yeah, and the leading bits could all be zeros. But let's just say that the numbers, like the way you wouldn't say the number 0, 2 in decimal. Yeah, you'd say the number 2. So let's just create some binary numbers, what they might look like. So you might have 1, 1, 0. That's a valid binary number because the digits in it are taken from this particular set. You might have 1, 1, 1. You might have 1, 0, 0, 1. These are all taken from this particular set of numbers. So these are all valid binary numbers. But hang on. If you look at the octal system here, so octal numbers, okay, uh, a valid octal number would also be 110 because that number, these digits are taken from that particular set. So this is nice where we have a little bit of ambiguity coming into play here. And to, I suppose, to differentiate between these numbers and the systems that they're from, now, when we're dealing with base 10 numbers, we don't. We're just the natural numbers that we deal with in the real world. Yeah. We're consciously aware that we're in that particular number system. Yeah. And it's very rare in the real world that we'll jump out of it. But obviously in the world of number systems, yeah, and especially in computing, we could be jumping across systems. So to differentiate that this number is a binary number, we usually put a little subscript 2 here to indicate that these numbers are base 2 numbers. Subscript 2, subscript 2. If I want to indicate that this is an octal number, I'd have a subscript 8 here. Yeah. But other octal numbers could be 3, 4, 5. Oh, it could be 1, 1, 7. It could be 7, 1, 5, because all these digits are coming from this set. And once again, these do look like decimal numbers, but if we put a small subscript 8 here, we now know definitively that these numbers are octal. And then our decimal numbers are decimal. Let's say our decimal numbers look something like this. So you choose anything from this particular set here for decimal. So you could have 110, €110, if that makes sense. You could have 3, 4, 5. You could have 6, 7, 8, 2, 10001. Once again, the ambiguity can creep in. Now, in this world, in the real world, we never put a subscript 10 here, but maybe we should if we want to differentiate these numbers from the other possibilities. And then finally, we have hexadecimal numbers, hex numbers are numbers made up of these digits. Yeah. Now, in a moment, I'm going to get back to talk about what these actually really represent from a positional number system perspective. Yeah, because that's what we're dealing with. These number systems are called positional number systems. Yeah, every digit has a meaning in its place within the number. Okay? If we go back to what I really mean, if we go back to primary school, we remember in primary school we had units, tens, hundreds, and thousands. Isn't that right? Okay. And we used to say how many units we had, how many tens, how many hundreds, and how many thousands we have. And we're back to early days in primary school, I believe. And that's what we mean by positional number system, is that the digits 2, 3, 7, 5 was 2,000s, 300s, 7 tens, and 5 units, yeah, which is 2,375. Yeah, that's what I mean by this positional number system, is that every digit has a meaning within the number, right? So hexadecimal, oh, that's still very loud. I don't know why that's so loud there, right? Um, hexadecimal number systems, yeah, are numbers taken from this set here. So we could have also 110, and we could have 2, 3, 2, 3, 4, 5, and we could have 6, 9, 7. Oh, and let's use some of these. We could have A, B, 3, 5. Okay. And what the hell do these represent? Well, this is what we really need to get to. Okay. So What we'd like to be able to do, and what this particular session uh, is really all about, okay, it's all about converting between number systems. Okay, it's converting uh, between binary and octal, and binary and decimal, and binary and hex, and all the possible ways we could do this. And for this class, this first hour, yeah, I suppose I'm going to provide a way that's it is, and I use the word foolproof. I don't mean that in in any derogatory way. I just mean it's a way that will allow us to achieve our goal to convert between number systems, but it has a little bit of baggage associated with it. And what I really mean is this: is that what I'm going to show you is how to do, or what we're going to show how to do in this class. Our next live session, we'll do the optimal way. So what we're going to do in this particular class, maybe I'll just move this over here, is we're going to look at converting uh, a decimal number to binary. Okay. We'll also look at converting a decimal number to octal, and a decimal number. We'll look at converting a decimal number to hexadecimal. Okay. And then what we'll look at is we look at converting a binary number to decimal, okay, an octal number to decimal, and a hexa number to decimal. Actually, what I might actually do is, because I was talking about positional number systems, okay, I might actually just do this piece here first, and then from here convert in. So you can see now I can go from decimal to binary, decimal to octal. I can go from decimal to hex. Yeah. If I want to go from binary to hex with this system, this is where the baggage comes into play. I want to go from binary to hex. Well, I'll convert the binary to the decimal, and then I'll go from the decimal down to the hex, because we'll be able to do that. And that's the baggage that I'm talking about. Okay, guys. I see that there's 6 people online now live, so thanks once again for joining me. I'm just gonna pause. I have a tendency to keep talking and to talk fast. One of my colleagues did say to me there a while ago, so maybe I'll just ask the question. Is everybody still moving along with this and with what I've presented? Does it seem reasonable enough at this particular stage? So I'm just going to ask that question to you guys there. I don't know how we do a thumbs up. Maybe a thumbs up is a thumbs up. Can we do a thumbs up here? Maybe not. I'm looking at my emojis here. I don't see, where are the thumbs up hidden. I don't know where thumbs up is. Yeah. So okay. Boom, 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 boom. I don't seem to have a thumbs up. I have a smiley face. Yeah. If that makes sense, yeah, which means I'm all good on this side. Well, look, I'll just clear so far. Thanks, Christoph, for that. So maybe what I'll do is I'll just continue on now. Okay, I'm going to need a calculator. Now, here at the National College of Ireland, and especially not for all modules, for these particular modules that are dealing with number conversions, you're not allowed to use a scientific calculator in exams. But I don't have any other calculator here, which is strange for a math support service. I don't have an accounting calculator or some other sort of calculator. We lend these things out, and they never come back. So what I'm going to do is let's take our first number, let's take a binary number, and let's convert it. Okay, let's convert a binary number into decimal. Okay, so I would just take any binary number. Let's say the number is 1 0 1 1. Let's say 1 1 0 1. This number is an 8-bit number. Okay, so this is, oh, I should put 2 here because this is base 2. So this is an 8-bit number, because there's 8 digits in the number. Okay, and typically when we're dealing with binary and octal, we would have some amount of powers of 2 as in relation to the number of bits that we present. But this number is an 8-bit number at this particular stage. And like what I said in relation to the decimal number system, the decimal, okay, and positional, okay, each digit represents something with respect to the base. It represents how many powers of 2 the actual position represents, if that makes sense. Yeah. So the first one, okay, like in when we have units, tens, hundreds, and thousands in decimal. But if you think about thousands, is how many 10 to the powers of 3s there are in the number. Hundreds are how many 10 squareds are in the number. Tens are how many 10 to the ones are in the number. And you probably get you see the pattern 3, 2, 1. Oh, that's it. Units are 10 to the power of zeros, because 10 to the power of 0 is actually equal to 1, which represents units. So in binary, each position represents multiple powers of 2. So this represents how many 2's to the 0s there are. This represents how many 2's to the 1s, 2 squareds, 2 cubes, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. Okay? So this number has 1 2 to the 7. It has no 2 to the 6's. It has 1 2 to the 5. It has 1 2 to the 4. It has 1 2 to the 3. It has 1 2 to the 2. It has 0 2 to the 1s. And it has 1 2 to the 0. And what I mean is, like the way we're saying that the decimal number 7,342 in decimal, that has 7,000s, which is 710 to the cubes, and it has 300s, which is 310 squareds, and it has 4 10s to the 1s, and it has 2 10s to 0. That's what we mean here. So effectively, this number here, which is now going to be a number in decimal, okay, is that this binary number is actually equal to, there's 1 2 to the 7, okay, plus there's no 2 to the 6's, but there's 1 2 to the 5, plus there's 1 2 to the 4, okay, plus there's 1 2 to the 3, here it is here, and there's one of them 2 to the, plus there's 1 2, there's 1 2 squareds, there's no 2 to the 1s, and there is 1 2 to the 0, okay, and each one of these represents something. Yeah, what does 1 2 to the 7, well, actually 2 to the 7, what is 2 to the 7? Just for you guys, this notation, 2 to the 7, it means it's 2 times 2 times 2 times 2 times 2 times 2 times 2. It's the product of 7 2's, okay, which is 2 2's is 4, 8, 16, 32, 64, 128. So I've got one of these 128, which is just 128. Plus, I've got 1 2 to the 5. Well, 2 to the 5 is simply 2 times 2 times 2 times 2 times 2. Okay, it's 2 to the 5, which is 2 2's is 4, 8, 16, 32. So I've got one of those, okay, which is 42. Plus 2 to the 4, well, 2 to the 4 is 16. 2 2's is 4, 2 4's is 8, 2 8's is 16. So that gives me 116. Plus 2 to the 3 is 8, so there's one of them, plus 8. Plus 2 squared is 4, and there's one of them, which is 4. Plus, well, there's 1 2 to the 0. And any number raised to the power of 0, x to the power of 0 is simply equal to 1. Right? That's an important identity for us. Okay, so it's equal to 1 here because it's one of them. So now what do we have? Well, if you look at the number here, let's just grab our calculator, so no errors. 128 plus 32 plus 16 plus 8 plus 4 plus 1 gives us 189 in base 10. Okay, so let's just write this down. So the binary number 1011 1101, this number here, base 2, converted to decimal, okay, is the number 189 in base 10. Okay, and that's effectively it. That's how you convert to decimal. That's how you convert all numbers to decimal. So let me just do one more example, but this time let's take an octal number. Okay, so let's take an octal number, and let's follow the same process. So what we had there a moment ago was binary to decimal. So now let's just take an octal number. Now we know an octal numbers are numbers that are based off this particular set of digits here, okay? The digits 0 to 7 inclusive. So let's look at the octal number. Let's say the octal number. So now we're going to go from octal to decimal, okay? And what we're going to consider is the octal number 7, 2, 1, 0, and let's say 3. All of them digits are in the octal base, yeah? So let's say this is small a here. We want to convert this number here, okay? We want to convert this number to decimal. So once again, like the way we said, the thousands, hundreds, tens, and units, each one of these digits has a meaning in its position, right? And its position represents how many multiples of 8 there is, right? So this 3 here represents how many 8s, its units, how many 8s to the zeros. This 0 means how many 8s to the 1s. This is how many 8 squareds. This is how many 8 cubes. And this is how many 8s to the 4s. Right? Every number represents something in the positional system. Okay? I'll need my calculator now for this. So effectively, this number here is equal to, there's there's 7 8s to the 4s. Now, earlier on with our binary system, because there was you only had one or 0 of the numbers in the system. Yeah. Okay. Now we have there's 7 8s to the 4. So this is 7 times 8 to the 4. Plus there's 2 8s, 8 cubes. Okay. Plus there's 1 8 squared. There's 1 8 squared. Plus there's none of them, but there's 3 of them. There's 3 8s to the zeros. Okay. Now, what is 8 to the 4? Okay, well, 8 raised to the power of 4 is 4,096. And there's 7 of them. So that's 7 times 4,096. Okay? Plus, what's 8 cubed? Well, 8 cubed is 512. So there's 2 of them. So it's plus 2 512s. Plus, there's one of these. 1 8 is 64. So there's 1 64. Plus, there's 3 of these, which is 3 times 1. I should keep looking up on the screen there to make sure that there's no major questions there. No, I think I'm all good now. There's no questions at this particular stage by the looks of it. Yeah, okay, which is good. Okay, which I'm assuming that people are keeping with me with respect to this process. And let's continue. So I'm going to refresh over this now in a second again. Yeah, so it's 7 times 4096 plus 2 times 5112, right? Plus 1 times 64 is 64, plus 3 times 1 is 3, gives us the number 29,763. Okay, that's in base 10. Excuse me. So the number 72103 in base 8 represents 29,763 in base 10. Okay. Now let's do something a little bit trickier. Well, we don't want to convert from decimal to decimal. That's straightforward enough. What about now from hex? This is the interesting one. From hex to decimal. Okay, so we want to convert from hex to decimal. Yeah. Now, let's think about this here for a moment once again. So we need to choose a hex number. So our hex numbers, our hex numbers have to come from this base 16 set here. So let's just choose some of them. Some from 0 all the way up to F inclusive. So let me just choose one of them. I won't choose something too crazy. Maybe. Let's say I choose 2, 3, A, let's say 6B, okay, and this is in base 16, okay, this is in base 16, and what I want to do is I want to convert this number to decimal. Once again, this is a positional number system. It's in base 16, so every digit represents how many powers of 16 there are, okay, so the first digit, the least significant digit, the most significant digit, okay. If I owe you €1,000, let's say if I owe you 2,375, what you're really interested in is this 2,000. You're not really interested in the five too much. Right? So from a base system, a positional system, this B is how many powers of 16s there is. Right? This is 16s to the ones, 16 squareds, 16 cubes, 16s to the 4. Okay, so you can see that this number has 2 of these. There's 2 16ths to the 4s in this. So let's just write it down as is. There's 2 of them. Plus, there's 3 of these. There's 3 16 cubes. Okay. Now, plus, there's A of these. There's A of them. What does A represent? If you think about it, okay. 9 represents that there's 9 of something. So A represents that there's 10 of something. A represents that there's 10 of something, 11, 12, 13 of something, 14, 15 of something. Yeah. And that's what we mean when we start adding in these digits. These digits now, these A's, B's, C, D, E, and F, represent these magnitudes, if that makes sense, how many of something there is present. So we can see that A represents that there's 10 of them. So we must have that there's 10 16 squareds. Okay, that's 10 16 squareds. And there's 6 16s to the ones. And there's B of these. So once again, there's B of them. There's B 16s to the zeros. Well, look at there's 0, 1, all the way up to 9. That represents 9 of something. A represents 10 of something. B represents 11 of something. Okay, so that must be plus. There's 11 16s to the zeros. Okay, so let's just do this out. And then what we have is let's just do this out. This is just 2 16s to the 4s. So 16 raised to the power of 4 is quite a big number. It's 65,000. So this is that there's 2 times 65,546 plus. So you can see actually that this hex number, although it's quite small, represents a big quantity in decimal. Yeah, that's the power of hex. You can represent more of something with less with less space, if that makes sense. Yeah. So now you can see there's 3 of these. So 16 cubed is equal to 3. So there's 3 times 4,096 plus there's 10 of these. So we have 16 squared gives us, 16 squared is going to give us a value of 256. So there's 10 256s plus there's 6 16s plus there's 11 ones because 16 to the 0 is equal to 1. Okay. And now just summing these up as we go through. So we have now 2 times 65,546 plus 3 times 4,096 plus 10 times 256 is 2,560 plus 6 times 16 plus 11 times 1 is just 11, which gives us a number of 146,027 in base 10. Now, guys, okay, so that's our conversions now, converting. So that took about 26 minutes. So we're doing well here. I think this will work now within the hour. Yeah, is converting now from each one of our systems into decimal. Okay, so if you think about it, actually, I could create a new base system just to show you the way this works. I can create any base system. Let's say we have base 18. Okay, so what does base 18 look like? It has to have 18 digits. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Then we have, that's 10 digits. So we need another A, B, C, D, E, F. That's 6. F, G, H. If I'm not mistaken, that's 1, 2, 3, 4, 5, 6, 7, 8. That's what base 18 would look like. And numbers in base 18 are taken from here. It's a crazy base. I haven't seen that being used. Okay, so here's base 18, the base. So just to show you the process again, I can choose any number, any digit. So let's say we have 2, 3, E, let's say 6, and G is the number in base 18. And I want to convert this to, because it's base 18, I want to convert it to decimal. So I want to convert this number to decimal. Once again, it's positional. Every digit represents something. It represents how many multiples or many powers of 18 there is. So this G represents how many 18s to the zeros, 18s to the ones, 18 squareds, 18 cubes, 18 to the fours. So effectively, this number has 2 18 to the fours plus 3 18 cubes plus E 18 squares. But what is E as a magnitude? Well, 9 is 9 of something. A is 10, 11, 12, 13, 14. So it has 14 18 squareds, okay? Plus 6 of these, 6 18s to the ones. And finally, plus, well, what's G? G as a magnitude? Well, I like to start here with 9. 9 represents as 9 is something, 10 of something, 11, 12, 13, 14, 15, 16. So there is 16 18s to the zeros, yeah, which we might as well just do this. Yeah, this gives us a number, and I'll do it all out, yeah, which is 2 times 18 square, 18 to 2 times 18 raised to the power of 4 gives us 209,952 plus 3 times 18 cubed gives us 20,577, okay, plus 14 times 18 squared gives us 4,546 plus 6 times 18, okay, gives us a value of 108 plus 16 times 18 to the 0 is 1. 16 times it gives us 16. What do we end up with? We end up with a nice number. It's 209952 plus 20577 plus 4536 plus 108 plus 16 gives us the number 245,189 in base 10. Okay. Now that's a crazy base. My point I'm trying to make is this: is that these positional number systems, which are the number systems that we typically deal with, okay, They represent each digit in the number has a meaning with respect to its base. Yeah. Okay. And this all goes back to that primary school when I'm going back here, yeah, when we've talked about units, tens, hundreds, and thousands, and so on. Each digit represented how many powers of 10 there was. Okay? So let's convert back now. Okay, so let's this time go from decimal. Let's say we want to go from decimal to binary. Okay, so we want to go from decimal to binary. And what I'm going to do is I'm just going to take the binary number that I had earlier, just as a sanity check to make sure we are doing this right. Okay? The binary number that we started with earlier, okay, was the 8-bit binary 10111101. And that number we converted to the decimal number 189. So really, I want to go backwards. I want to do the process how to get from 189 to this number here. Okay, so I want to go from 189, 189 using binary to a binary number. Now the binary is base 2. Okay, so let me just fix this here. Oh, this on my screen is coming up reverse, so anytime I have to do things opposite. So this is base 2. So we want to go to base 2. Okay? We want to go to base 2. So what we should do is this, and here's the process. Yeah. Okay. Okay. This is the division algorithm. This is once again back to primary school. There's so many fundamental things that we did in primary school. Yeah. And there was one thing called the division algorithm. Yeah. Like for example, maybe if I asked you what's 7 divided by 2. Now, in our world, we might actually get a calculator out and we might actually go 7 divided by 2 gives us, well, it's 2 and 1/3. As a decimal, it's 2.3333. Yeah. But I'm not really interested in that. I'm interested in the rhyme in school. Okay. 7 divided by 2. Or would I be better off saying 2 divided into 7? Yeah. So 2 goes into 7 3 times with a remainder of 1. Yeah. What did we mean by that? Okay. Well, what we really meant by that was, so when I divide 2 into 7, I say it goes 3 times with a remainder of 1. Okay. What the hell does this mean? Well, what it really means is this, is that 7 is equal to 3 times 2 plus 1. Okay. Okay. When I divide 2 into 7, this is called the division algorithm. Yeah, the division algorithm, yeah, is something that we learned in primary school, although it wasn't represented like that. So what we're going to do is we're going to take 189 and we're going to keep dividing it by 2. Okay. And we're going to keep track of the remainders, okay, on each division, and also how many times the number divides into the number, if that makes sense. And this is what's going to allow us to construct this binary representation of 189. Sounds complicated initially, but you'll see now. And this is, I really need my calculator for this, yeah, so that we keep track of this. So what I'm going to do is I'm going to take 189, okay, and I'm going to do the division like this. So once again, the whole style of dividing, yeah, I'm going to divide by 2. Okay. So you think about it. 2 into 1 won't go. 2 into 18, well, 2 into 18 goes 9 times. 2 into 9 goes 4 times with a remainder of 1. Okay. So this is my first remainder. Yeah, this is important. This is actually what's known as my least significant digit. Okay. We'll get back to maybe later on why that actually is the case. Now I start the process again. I take 94 and I divide by 2. 2 into 9, well, 2 into 9 goes 4 times, but there's a remainder of 1, so we're going to carry forward 1. Okay. Don't forget that 1 represents a 10. Yeah. So that gives us 14 here. So 2 into 14 goes 7 times, but no remainder. Okay. I do it again. 2 into 47. 2 into 4 goes twice, no remainder. 2 into 7 goes 3 times with a remainder of 1. I do it again, and I'm going to continue this process. And you can see that this particular sequence is getting smaller and smaller and smaller. Eventually, it's going to have to end up as 0, which is a consequence of the Euclidean algorithm, which is multiple applications of the division algorithm. Yeah, but we're not really interested in that. So I'm going to divide this by 2. 2 into 2 goes once. 2 into 3 goes once with a remainder of 1. I'm going to divide 11 by 2. Okay. 2 into 1 won't go. 2 into 11 goes 5 times with a remainder of 1. 2 into 5 goes twice with a remainder of 1. And I'm going to divide 2 into 2 goes once with a remainder of 0. And then I'm going to divide 2 into this. 2 into 1 won't go with a remainder of 1. Okay. And that's it. When we get to zero, we stop. And this number here is our decimal, is our binary number. Then this is the most significant digit. Okay? And if you think about it, we usually do it in blocks of 4. So the first block of 4 is here, and the second block of 4 are these 4 numbers here. Least significant digit first. So it's 1 followed by a 0, followed by a 1, followed by a 1, followed by a 1, followed by a 1, followed by a 0, followed by a 1. And this is base 2. Okay? And that is exactly what we started with earlier on. 1 0 1 1 1 1 0 1. 1 0 1 1 1 1 0 1. Okay. What about let's see, where am I gone to? What about now when we're dealing with, let's say, octal? Okay, so let's take our octal numbers. Yeah. Okay, let's take a decimal number and convert it to octal. Right. 189 being converted to base 2, I successfully divide by 2 and kept track of the remainder. If it was 189 going into octal, I'd keep dividing by 8. But let's use the example that we had earlier. Okay? So what I'm going to do is I'm going to take this example here, which is the number that we ended up with was 29763. Okay? So we had so the number we started with was 72103 in base 8 was converted to 29763 in base 10, and we want to convert back the other way. So I need to start with this number. So let me just write that down here. So we're going from decimal to octal now. Right? So we got 29763 in base 10. I want to convert to base 8 to octal. So what do? Well, we take our number and we keep dividing by 8. Yeah, keep that division algorithm in mind. So now we take our number 29763 and we divide it by 8. Now this is where the calculators come in handy. Okay. So if you think about it here, 29763. I'll just bring this up here so that we can sort of see it. Maybe, oh, where am I going? Okay. 29763 divided by 8. Okay. It actually goes 3,720 times with a certain amount over. So let's just keep track of that. 3,720 times. So it goes 3,720 times. And there is a remainder. Okay. What's the remainder? Okay. Well, if you think about it, what we're saying is that 29763 must be equal to, well, it must be equal to 8 times 3720 plus some remainder. That was what the division algorithm was all about. And what is the remainder? Well, the remainder must be equal to 29763 minus 8 times 3720. If I take this and bring it over this side of the equals, it flips side. Okay? So now we have 29763 minus 8 times 3720 gives us, oh, it is a remainder of 3. Okay? We take this number now and we divide by 8. So let's do that again. So now we have 3720 divided by 8. Okay? Gives us, it goes 465 times. There is no decimals, there's nothing, it goes that perfectly. So it goes 465 times. So the remainder must be 0. Okay? So the remainder must be 0. Then we take this number here and we divide by 8. So let's take 465 and divide by 8. And you can see in this situation, there is a decimal. It goes 58 times. Okay? 58 times with some remainder. What's the remainder? Well, what are we saying? We're saying 465 divided by 8 goes 58 times. So 465 must be equal to 8 times 58 plus some remainder. What's the remainder? The remainder must be 465 minus this piece here. Okay? So now we have 465 minus 8 times 58 gives a value of 1. So the remainder is 1. And we do it again. So we divide 8 into, so we're going to divide 8 into 58. So we have 58 divided by 8 goes, you can see that goes 7 times. Okay. So it goes 7 times. If you think about 8 sevens is 56. So the remainder must be equal to 2. Okay. The remainder must be 2. And then what we do here is we divide our 8 into 7. It won't go, but what's left over is the 7. And once again, this is our least significant digit. This is our most significant digit. And the number that we end up with is, from a least perspective, 3, 0, 1, 2, 7. And this number here is in, well, we've gone to base 8. So this is in base 8. Okay, guys. The final thing now to do. I'm getting close to the time here now, but let me just do now the most important one. Well, which is usually the tricky one for us, yeah, which is the hex. Okay. As an example, I want to go from hex to I want to go from decimal to hex. Okay. So I want to convert from decimal to hex. I'll just move this out of the way here, and let's use the example that we had earlier. Okay. So I went from 23A6B as my hex number. I went from there into 146027 base 10. So I want to go from decimal to hex, and the number I want to convert is 146027. I want to convert that to base 16. And like everything else, whatever base you want to go into, we're going to keep dividing. We're going to keep dividing by that value. So we're going to get 146027, and we're going to divide it by 16, and we're going to see how we get on here. Okay, so we have 146027 divided by 16. There you go. It goes in 9,126 times, with a little bit over, a fractional amount over, yeah, okay, with some remainder. What's the remainder? Well, let's write that down again. So we must have had 146027 must be equal to 16 into it goes this amount, so there must be that amount in it. 16 times 9126 plus the remainder. Bring this over, it becomes negative. Take this away from this. So effectively, we have 146027 minus 16 times 9126 gives us a value of 11. So the remainder is 11. Yeah. Divide this by 16. Okay. So now we have 9126 divided by 16. It goes 570 times. What's the remainder? Well, the remainder must be 9126 must be equal to 16 times 570 plus a remainder. So we take this away from that. So we have 9126 minus 16 times 570 gives us a value of 6. So the remainder is 6. Okay? And we continue. We're going down. We're continuing to divide this by 16. So we have 570 divided by 16. It goes 45 times. And the remainder is going to be, well, 570 is equal to, well, 16 goes into 45 times, so there must be 16 45s in it, okay, plus the remainder. And the remainder is going to be, bring this over and take it away, so it's 570 minus 16 times 45 is equal to the remainder. Okay? That was the first and the second one. This is the third one here. So now we have 570 minus 16 times 45 gives us a value of 10. And then what we're going to do is we're going to take 16 into 45. You can see that that's going to go twice, yeah? 2 16s is 32, so that leaves us with a remainder of 3. Okay? Then we're going to divide 16 into 2, won't go with a remainder of 2. And this is our most significant digit. This is our least significant digit. Yeah? And don't forget, these things are digits in our system. Now, our digits in our system, the hexadecimal system, let me go all the way back. Where am I gone to? The digits in our hexadecimal system are only zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9s, A, B, C, D, E, F, and so on. But these are magnitudes. There's 11. Well, 11 in our system represents a B. Am I not mistaken there? 11 in our system represents a B. And this is a 10, digit 10. So this is an A. That's an A in our system. So actually the number, this is a B, and this is an A. So actually now the number is, the least significant digit is B, followed by 6, followed by A, followed by 3, followed by 2. And this number now is in base 16. Okay. Whoa. Right, guys. Look, I know there's a lot to take on board here, but I suppose the key thing here is that this video now will be up online, and you'll be able to maybe go back through this. Also, I can take questions. Yeah, if you want to send them questions to my email address, I can take some more questions. Unless there are specific questions here. As I said, all this was going to do this video today, yeah, was to allow us to be able to convert. Let me just go back here and find that template that I had started with from a conceptual perspective. What we were interested in was, I'll just get rid of this here. We're interested in being able to convert from any one of our number systems. Yeah, just ignore this. From any one of our number systems to decimal. That's very easily done because that's the positional system. Okay, and then to go from decimal to any one of the other systems. That's through the successive divisions. To go to binary, to keep dividing by 2, keeping track of the remainders. To go to octal, we keep dividing by 8, keep track of the remainders. To go to hex, we keep dividing by 16. Okay? To go to base 18, okay, base 18 from decimal, we keep dividing by 18, keeping track of the remainders. Okay, so you can see now that you actually have access to any number system, any positional number system, if that makes sense. Right? Okay, guys. What I'm going to do is I'm just going to maybe just ask you guys the question, because this was my first session. Uh, how was that for you? Did that help? Do you think that this video, if I leave this video up online, do you think that that might help you in relation to this particular topic? So that's a question I'm just going to fire out to the 7 people that are actually there now. So hopefully, we'll see what the answers is. Yeah, so maybe I'll ask that question. Yeah. Hi guys. Um, uh, did this work? I suppose is the question. Yeah, I really need to. I'm going to ask you here. Did this work? Edward, I don't know whether you're there. Oh, Edward, you haven't got an account yet, but I'm going to ring you now in a few moments because I know that a student of mine is there somewhere watching this. So maybe I should give a shout out to Edward there. Yeah, and thanks for watching. I did say I'd ring you at the end of this, my first live session, to see what you thought of it and whether this was helpful in any way. Okay, we'll just give it another second or two. So Owen, thanks Owen. Oh, brilliant. Okay, excellent. You were able to write notes when you were going along. That's brilliant news. Okay, brilliant. I am sort of conscious. I have got this conscious thing that I do talk very fast. Yeah, and I am conscious. I have to try to maybe slow things down a little bit. Schler, hopefully I pronounced your name right. Thanks very much. Brilliant, and thanks for watching. Okay. Okay, guys, I think I'll end there. And the plan is at this particular stage, and I'm actually going away next week. Yeah, so the plan is going to be, I think I'm going to have another session this week. I think I'm going to have the session and run it on Friday of this week. So I'm going to run it on Friday of this week at probably the same time. Okay. Next week I won't be live at all, and I'm going to try to make sure that I have a regular session going on. That deals with questions that students have asked me through YouTube and also through NCI here. Okay? So once again, guys, thanks for watching. I hope this was intuitive, and more importantly, I do hope it was helpful for you. And thanks for watching. Maybe I could actually throw a plug in there. I do have a playlist that deals with number conversions. So all of this stuff I have done through a playlist before, but it wasn't a live stream. Okay? So guys, thank you. Okay, bye bye. Oh, just have a question here now. Was this recorded? Severin, yes, this was recorded. I'll just respond to you here. Hi, Severin. Yes, this was recorded, and will be available on the on this YouTube channel. So once I hit end stream here, YouTube take over. YouTube do a little bit of processing on it, and then it will go live. I think what I'm going to do is I'm going to put this into a new playlist called live streams, so you'll be able to access it in that particular playlist. Yeah, if that makes sense. But it's also going to be on my latest uploads as well, which is on the main main page. Okay. Any other questions there before I head off? Everything seems good. Okay, so maybe I'll just end there. Okay, thanks for watching, guys, and hope to see you all soon enough. All right. Okay. I'm going to end this now. Okay. There we go. End the stream.